This is lecture 18, where we're going to do a bit more on permutations. We've got one new handout, that's next week's lectures and workshop, and some spares of today's lecture as well. The spares are on the desk near this end. Right, okay. So it was probably new to you last time how to multiply permutations, or even what permutations were. But I don't think you found it very hard. Multiplying permutations is quite an easy mechanical activity. Usually you get different answers when you do them in different orders. As last time we multiplied a couple of permutations in two different orders and we got two different answers. So that's what typically happens. But sometimes you get the same answer. And here's an example where you get the same answer. I will tell you what the answer comes out to be. And there's a particular reason for it. You see, 1 doesn't get moved by Tor, but it gets sent to 7 by sigma. But 7 doesn't get moved by Tor either. So 1 goes to 7 whichever way you do it. 2 doesn't get moved by sigma, but it does get moved by Tor to 6. 6 doesn't get moved by sigma either. So either way around you do it, 2 ends up at 6. 3 does get moved by sigma, it sends it to 1, but it doesn't get moved by Tor. 1 doesn't get moved by Tor either. There's no coincidence here, so 3 ends up at 1. 4 ends up at 3, 5 ends up, doesn't get moved by sigma, but it gets moved by Tor to 2. 6 doesn't get moved by sigma, but Tor sends it to 5. And 7 doesn't get moved by Tor, but it does get moved by sigma to 4. And you can check that both of these, this is equal to the thing either way round. So there's obviously something unusual about these permutations. And the unusual thing is, as we're going to see in a minute, if you find something that does get moved by sigma, then it doesn't get moved by Tor. And anything that does get moved by Tor doesn't get moved by sigma. They are what's called disjoint permutations. That's what we're going to talk about. So here's what it means to say that two permutations are of a finite set, or indeed you could do this for an infinite set, but we're only really interested in finite sets in this module. So two permutations of a finite set are disjoint, or we could say mutually disjoint, means that if you look at any x in your set, then at least one of them leaves it where it is. So at least one of sigma of x is x, or Tor of x is x. In other words, if sigma of x isn't x, then Tor of x does have to be x. And if Tor of x isn't x, then sigma of x has to be x. And that's what it means to say they're disjoint. It's, you see, you look at where these permutations actually doing anything. It's not very interesting where they're leaving stuff the same. So you look at where they're actually doing something. And if there's no overlap between those, then they're disjoint. So set notation, you look at those x's which are moved by sigma. You look at those x's which are moved by Tor, they shouldn't overlap, right? So it's a different set of things that get moved, if there are any that get moved at all. Okay, there's no overlap at all between the what you might think of as, I'm not sure if support is the right term. I have to look that up, what the name for that set is. Anyway, so those permutations we had before, as I pointed out, they were disjoint. And we're going to see in a bit that that always means that it doesn't matter which order you multiply them, you get the same answer. And yes, you can do it for infinite sets, but we're not very interested in infinite sets. At least we're not very interested in permutations of infinite sets in this module. So here's an exercise for you. And it actually, it turns up on one of the question sheets as well. Pretty much. So in disguise, So the trick for this exercise is because f is a bijection, f is the inverse of its inverse. And that means that f of a set is equal to f to the minus 1 to the minus 1 of that set. Except that you can think of f to the minus 1 as a function, and you can think of the other minus 1 as making it into pre-image, because we said earlier that you get the same answer. So in fact, if f is a bijection, then images of sets are also pre-images using the inverse function. And pre-images are better than images, as you'll have seen on one of the question sheets. So the image of the complement is usually not equal to the complement of the image. But the pre-image of the complement is always equal to the complement of the pre-image. But if you have the bijection, then the image is a pre-image. So then, when you're a bijection, the image of the complement is equal to the complement of the image. And so that's a nice thing that happens with bijections. And since we're dealing with permutations, permutations are bijections, and so that will be available to us. So when we're working with permutation and we want to see what does it do to the complement of a set, it sends it to the complement of what the thing does to the set. And using that, we can prove the following lemma, which will help us prove what we want to about disjoint permutations. Now, this A then, and I've said a finite set X, but actually it works for infinite sets as well. And the proof I'll give you will work for infinite sets as well. But there are lots of proofs of it around. We don't really need the full force of this, though it sort of comes to free. What we really need is that the permutation maps this set into a subset of itself. Since we're dealing with finite sets, that's actually the same thing, because it's a bijection, and if it maps a set to a subset of itself, and the set is finite, then it's going to have to be the whole of it as well, because it doesn't change the number of elements. If you want to do it for infinite sets, you have to work a bit harder. But what we really want in a moment is to know that sigma of A is a subset of A. Never mind, we'll prove that it's equal. And so this is a set of things that are moved by sigma. And what we'll do is we'll look at the complement. So set B equals A complement equals X in X, for which sigma of X equals X. Those are the things that sigma doesn't move. Now, sigma of B is obviously equal to B because sigma doesn't move anything in B. But if you wanted to write it in full, sigma of B has got to be B because things don't move. But definition of sigma of B, that's the set of all sigma of X's where X is in B. But if X is in B, then sigma of X equals X. So I can just change that sigma of X into an X. That's by definition of B, which is B. Okay. But now sigma of A is B complement. That's sigma of B complement. And since sigma is a bijection, that's equal to sigma of B all complement. That's because since sigma is a bijection, but sigma of B is B, so that's just B complement by above, which is equal to A. Okay, so that's one of dozens of different ways to prove this thing. I shall let you think up some more proofs for yourself. Another way of thinking about it, morally speaking, is A is a set of things that are moved. Sigma is a bijection. If you take something that's moved, the place it goes to has got to be moved as well, because if it was staying in the same place, sigma wouldn't be injective. Also, this thing that's moved must come from somewhere that's been moved, because it's not coming from itself, because it's gone somewhere else. And sigma's surjective, so it must come from something else, which has therefore been moved. So you can argue it that way if you like. You could go through a case-by-case analysis and just think, if you're in A, notice you're sent somewhere else, and that thing that you're sent to has got to be sent somewhere else again, and you must have come from somewhere that was sent somewhere else. So that's another way of doing it. So I'll let you think about that. But anyway, so as I say, in a moment we're going to use the fact that it's really what we're going to use the fact is a bijection maps, a bijection from a set to itself maps the things that get moved by the bijection into a subset of the things that get moved. It happens to get to all of them, but that's less important. So now, suppose you've got mutually disjoint permutations with a finite set, then I'm going to prove, and it works for infinite sets as well, they'll prove that they multiply correctly either way around. So what we do, we set A to be, so it's slightly different this time, different A and B this time. A is still those x in x for which sigma of x is not equal to x. And B will be x in x for which tor of x is not equal to x. And because they're mutually disjoint, those have no intersection. Since they're disjoint, A intersection B is empty. We may need the rest of the set as well. Set C equal X, take away the union A union B. Let's have a bit more room. Okay, so X is the pairwise disjoint union of these three sets. So X is equal to A union B union C, and these three sets are, it's a pairwise disjoint union. None of those three sets overlap with the others. That's not a very good pairwise. I'll just try that again. Right. Okay. So if you're an X, you're in exactly one of these three sets. And we'll just do a case-by-case analysis of what sigma tor and tor sigma do in the three cases. Now, A, those are the ones that are moved by sigma, and they're not moved by tor because nothing's moved by both. B are the ones that are moved by tor, those ones aren't moved by sigma. And C are the ones that aren't moved by either. And if you start in C and you do sigma tor, you stay put because neither sigma tor moves you. You do one of them, you haven't moved, and then you do the other one, you still haven't moved, so you're exactly where you were before. So let's look at these three cases. So let X be in X and investigate sigma of tor of X. Remember, that's how you multiply the permutations, and tor of sigma of X. So case 1, I'll do the easy case, is where X is in C. Then sigma of X equals tor of X equals X. C are the ones which aren't moved by either. And then sigma of tor of X is equal to tor of sigma of X equals X as well. Okay, so C is pretty boring. neither permutation moves you, and you stay put when you apply both permutations in either order. And now we've got to look at A and B, which are similar, because it's symmetrical between sigma and tau, this. So case 2 is x is in A, then sigma of x is not equal to x, but tau of x equals x. Okay? X is moved by sigma, but is not moved by tau, because they're disjoint permutations. But moreover, sigma of x is not moved by tau either. And that's because sigma of A equals A. So we know that if something is moved by sigma, then it's moved to something else that's moved by sigma. That's the main thing we need. So sigma of x is not in B. X is in A, so sigma of x is still in A, and therefore sigma of x is not in B, because A and B don't overlap. Sigma of x not in B means that tau sigma of x equals sigma of x too. Remember, B is the ones that are moved by tau, so if you're not in B, you're not moved by tau. So sigma of x not being in B means that tau of sigma of x is going to be sigma of x. And now we can put all that together. Tau of sigma of x equals sigma of x is equal to sigma of tau of x. So that's good. Got the same answer that way, because one of them, tau didn't move either of x or sigma of x. So that's why you still ended up at sigma of x either way round. Case 3 is identical. That's the last case. Otherwise, we must have x in B. But now we just use a similar argument to case 2. Now swap sigma and tau and A and B in the case 2 argument. I'll let you write it out in full for yourself. This time you get sigma of tau of x equals tau of sigma of x equals tau of x. It's symmetrical, this whole thing between sigma and tau and A and B. So you're finished. In all cases, sigma tau of x equals tau of sigma of x. In other words, remembering that we're talking about composing permutations. Multiplying permutations is composition, so they're equal. We've done it. Okay, any questions about that? You can try it out with as many different permutations as you like, just to check that it really works. So write down a few disjoint permutations, ones where to be disjoint, there mustn't be any element moved by both of them. Okay? They don't have to between them move everything, but they must not both move the same thing. Okay. So we go back to the same two permutations, which turned out to be disjoint and to give the same answer whether you multiply them in either order. these turn out to be rather special kinds of permutations called cycles. Okay, so if you have a look at what they're actually doing, sigma of 1 is 7. So 1 goes to 7. You look at where 7 goes, it goes to 4. 4 then goes to 3, and 3 goes back to 1. And it doesn't move anything else. So what happens is these four things get cycled, and the other ones stay where they are. If you do that sort of thing, you're said to be a cycle. And Tor is also a cycle. This cycle cycled 4 points round. This cycle Tor cycled 3 points round. 2 goes to 6, 6 gets sent on to 5, 5 gets sent to 2, and none of the others move. Now, every permutation is made up of a few cycles, we're going to see in a bit. But not every permutation is just a cycle. So these two are special. Sigma is what we call a 4-cycle, because it cycles 4 things. And Tor is what we call a 3-cycle, because it cycles 3 things. And we've got a notation for them. The cycle notation means, so here's sigma in cycle notation. This just means 1 is sent to 7, 7 is sent to 4, 4 is sent to 3, and 3 is sent back to 1. Okay? And it's just a short way of writing it. So that's all it means. And Tor sends 2 to 6, 6 to 5, 5 back to 2, nothing else moves. So it's a 3-cycle. Now, you can write them in a different order, and it's still the same cycle. Sigma here still says 7 to 4, like before, and 4 goes to 3, like before, 3 goes to 1, like before. Remember, you come back on the other end, and 1 gets sent back to 7, like it got sent to 7 before. So there's 4 different ways of writing the same 4-cycle, and 3 different ways of writing the same 3-cycle, and so on. So it's not that there's a unique way to write it, but there's no real difference between these. Okay, so these are all the same. If you want to change a 4-cycle on the same elements, you have to make a more genuine change to the order you've written them in, right? You're not allowed to, if you want to make it into a different one, you could do it. Okay, 7, 3, 4, 1 is different. Okay? Right? So some of these look different from each other, but they're the same, whereas 7, 3, 4, 1 is genuinely different because that sends 3 to 4 instead of sending 4 to 3. Okay? That's slightly different. 1 cycles are a bit boring. We do allow them, but okay, this is the cycle that sends 3 to 3 and leaves all the others the same. There's no real point in writing it down because that's the identity permutation. Okay? So, but you can write them if you want. And there are times when you might find yourself writing a 1 cycle, and it's usually optional whether you write them down or not, because they're the identity and they don't do anything. 2 cycles are very important, and they're transpositions. And it turns out that whatever permutation you've got, you can make it up by doing some transpositions, one after another. If you do several transpositions, you can get one after the other. You can get to complicated permutations, and every permutation can be got that way. And rather interestingly, there's a difference between those permutations you can get to by multiplying an even number of transpositions and those you can get to by multiplying an odd number of transpositions. Though it's not immediately easy to prove that you can't. You need some sort of a proof to show that there aren't any permutations you can get both ways. But there really aren't any permutations. There's no way that you can multiply an odd number of transpositions together and get the same thing as multiplying some different even number of transpositions together. So it's not that it's unique how you do it, it's just that it's always either an odd number or an even number, and that's called the sign of your permutation. That's quite useful, but we won't do that in this module. Okay, so look up the sign or signature of your permutation and you'll find interesting things about it. Okay, K-cycles do exactly what you think. You have to take some distinct elements of your set, A1, A2 up to AK, And then, as before, A1 is sent to A2, A2 is sent to A3, A3 is sent to A4, and so on. And AK is sent round again back to the beginning. You could think of them, if you really want, you could think of them as lying on a circle. Right? So you've got A1 is sent round to A2, is sent round to A3, and there's an AK that gets sent to A1, and AK minus 1, if there is one, is sent to AK, and so on. So that's the idea. Obviously, if K is less than 3, there won't be an A3. And if K is less than 2, then there's only an A1. But that's the idea. So they get mapped cyclically, one to the other, and no other elements are moved. Right? And that's a K cycle. So we've seen a 3 cycle, a 4 cycle. I've told you that 1 cycles are boring, and I've told you that 2 cycles are important. Here's a question for you. When you're counting permutations, a permutation is the same if it's the same function. So you can write different permutations in different ways, but it's still the same permutation. If you're counting permutations, you're only allowed to count each permutation once. Okay? So the fact that you write it in a different way is not going to give you more than one permutation. So the question is, how many genuinely different permutations are there of this H set, which are 3 cycles? And I'll give you a bit of time to think about that one and see if you can figure it out. Okay, so since the majority have asked me to explain the question again, I'll see if I can help you a bit further. So, first of all, I'll write down a couple of examples, like 1, 4, 6 is a 3 cycle. That's the same 3 cycle as 4, 6, 1. And that's the same 3 cycle as 6, 1, 4. So that only counts as 1. That's one of the 3 cycles that's available. Whereas 1, 6, 4 is different. That's the same as 6, 4, 1. It's the same as 4, 1, 6. Whoops. So that gives you one more, though that's a different from the other one. Notice this one sends 4 to 6 and 6 to 1. This one sends 6 to 4 and 4 to 1. So that's definitely different, okay? So these two are different. Those are the only 2 3 cycles you can make that are generally different if you're using 1, 4, and 6. Okay? Now, given that as a hint, that might give you one of the ways of doing it. So I shall pause the capture again and see whether that gives you a chance. Okay, let's see what people went for. So as I mentioned before, a lot of people went for explain the question again. Now I've explained the question again, and we've got quite a lot of answers, but the majority have gone for A, whereas this is not the correct answer. So the correct answer is C, 112. So let's see if we can see if I can persuade you why. I'll give you 2 arguments for this. Okay. One is you're looking for A1, A2, A3, and at first you think, I've got 8 choices for A1, 7 choices for A2, and then 6 choices for A3. So it looks like 8 times 7 times 6 choices for A1, A2, A3. which is true for the, if you care about the way you write it. But you get each of the 3 cycles 3 times this way. So you want a third of 8 times 7 times 6 to get the correct number, and that's 112. Or there are 8 choose 3 ways to choose your set A1, A2, A3 as your 3 set. 8 choose 3 3 sets. But that's only 56. However, having chosen the 3 set you're going to cycle, there are 2 different cycles. So if you choose 3 sets, so it'll turn out to be you get 2 cycles for each 3 set that you decide to cycle. So in fact, there are 2 free cycles for each 3 set. Or each 3 subset. And 2 times 8 choose 3 is also equal to 112, I'm pleased to say. Okay. Any questions about either of those ways of counting? If not now, you can always ask me another time. I'm always available for questions. Well, not always, but it's easy enough to find me. Okay, so moving on. Disjoint cycles. I told you already that sigma and tau were disjoint. It's even easier to see that they're disjoint when you write them as cycles. Okay? Because cycles, well, okay, there's a slight issue. The 1 cycles are a bit silly. Forgetting about 1 cycles, you can normally tell if cycles are disjoint if they don't mention any of the same numbers. 1 cycles spoil that, but ignore the 1 cycles and it becomes okay. We can see that the things moved by sigma are 1, 7, 4, and 3, and the things moved by tau are 2, 6, and 5, nothing in common, so they're disjoint. And that gave you sigma tau equals tau sigma. So if you multiply these cycles either way round, you get the same answer, and you get the permutation we worked out before, and that's sigma tau. Now, every permutation could be written as a product of disjoint cycles in pretty much a unique way, as a product of disjoint cycles. You can also write them as products of cycles that aren't disjoint. Like if you're going to multiply to the, if you're going to write them as a product of transpositions, 2 cycles, that's usually, that's very likely you're going to have to do that with some overlaps, and not disjoint at all. But the fact that every permutation can be written as a product of disjoint cycles, and that sort of tells you the shape of the permutation. The permutation may be got, if you're a big set, your permutation might be made up of 2 free cycles, a 7 cycle, a 20 cycle, and a 2 cycle, and leave everything else fixed or something. And the shape of your permutation is, tells you a lot of things about what how the permutation behaves. Right, so, but I won't prove that formally. I'll just do an example, and the example will make it pretty clear how you would make a formal proof if you wanted to. Okay, so let's have a look at an example. Consider the following permutation of an 8 set. Here it is, in 2-line form. Write it as a product of disjoint cycles. And you can, after you've done these for a bit, you can do it in your head. Here's a systematic way of doing it. And as I said, it's almost unique, but first of all, the cycles can be written in more than one way. And secondly, you can change the order you multiply them. But here's the most systematic thing you do. You say where does 1 go? 1 goes to 8. So I'm going to have to put an 8 after 1. Where does 8 go? 8 goes to 1, so I better finish that. That's a transposition. It's a 2 cycle. Now I've used 1 and 8, so I go to the first one that I haven't mentioned so far, which is 2, and see if it moves. If it doesn't move, you can write it as a 1 cycle, or you can ignore it. 2 gets sent to 6, so I better write that down. 6 gets sent back to 2, so it's another transposition. I better stop there. Okay, so 6 gets sent back to 2. Now we've used 2 and 6. So I think, what's the next one I haven't used? That's 3. 3 gets sent to 5. It'd be boring if 5 got sent back to 3. 5 gets sent to 4, so that's different at least. 4 gets sent to 3 again, so we can close that one up. And now we know where 3, 5 and 4 are going. What's the next one we haven't used? Well, we've now used 3, 4, 5 and 6. There's only 7 left. And since 7 is sent to 7, you can either ignore it or you can put it in as a 1 cycle. That's optional. Okay? Your answer is correct whether you do or don't put the 1 cycles in. And because they're disjoint cycles, you can multiply them in any order and you get the same answer. So it doesn't matter which order you write these down in, because they're disjoint. If they're not disjoint, it does matter, as I'm going to see in the final example. But this one is a pretty easy thing, and you can do this all in your head once you've done a few of them. It's such a quick, systematic operation. Any questions about what I actually did there? I think it's pretty clear. Okay. As I said, this always works for any permutation. You can always write it as a product of disjoint cycles. Yes, I could have written 6, 2 instead of 2, 6. I could have done 5, 4, 3 instead of 3, 5, 4. And I could have written them down in different orders, but otherwise it's unique. Oh, and the 1 cycles again. You can leave them out or keep them in. But otherwise it's unique. I do want to finish by pointing out that you can also multiply cycles together, because you can multiply any permutations together, and cycles are permutations. So even if cycles aren't disjoint, you can multiply them, right? And I'm putting this in this year because last year I didn't, and then when people got to mathematical structures, they got confused when they had to multiply permutations that weren't disjoint. You can multiply things that aren't disjoint, and it's very easy to do them. So I'll do that quickly. Remember, the one that's on the right gets done first. Okay? So you do this one first. If you're going to do that for this product, oh, fast. That would also be good, but I meant first. This time you do this one first. When you remember, you're composing functions, and that means the function on the right gets done first. So let's do the first one. 1, 5, 3, 6, 2, 5, 4. I'll do it in 2 line 4. Though you can go straight to disjoint cycles if you want, because you can do that in your head too. Let's see where 1 goes. Okay? You do the second. You do the right-hand bracket first, but it doesn't move 1. So I can say 1 is still at 1, and now I see where it goes now. It goes to 5. Now let's look at where 2 goes. I have to do the right-hand one first. So 2 gets sent to 5, and then I do the other one, which sends 5 on to 3. Now look at 3. 3 doesn't get moved by the right-hand one, so it's still at 3 so far, but when I come here, it gets moved to 6. Look at 4. 4 does get moved by the right-hand one, so I do that first. When 4 goes to 2, then 2 doesn't get moved by the other one, so I'm still at 2. Look at 5. I do the right-hand one first. 5 gets sent to 4. 4 doesn't get moved by the other one, so I stay at 4. and I look at 6, 6 doesn't get moved by the right-hand one, so I can pay attention to the other one, and 6, that's all right, but doing the right-hand one first, but 6 is still at 6. Then I go to the other one, and 6 is sent round to 1. Okay? And that's what you get when you multiply them that way round. But if I do them the other way round, let's see where they go in two-line form. So to be faster, 1 goes to 5, which is then sent to 4. 2 doesn't move, but then gets sent to 5. 3 moves to 6, which then doesn't move. 4 stays where it is, but then gets moved back to 2. 5 does get moved to 3, which then stays put. And 6 gets sent back to 1, which then stays put. And as you can see, they're different. So they weren't disjoint cycles. I multiplied them in the two different orders. You're allowed to do it, because you can multiply any two permutations, but you're likely to get different answers. Okay, so any questions about multiplying permutations or anything I've done? If not, then we'll start the workshop at 4.